Hello everyone, welcome to the ongoing video tutorial series on BWSim-5G simulator. In today's session, we will explore the concept of interference in wireless communication. Interference is a critical aspect of wireless technology that can affect the reliability and performance of your wireless networks. 5G networks are like a grand orchestra of networks where you have networks of networks comprising furthermore networks all working together to make use most of their resources. In the past, to prevent interference between cells, network had to maintain a kind of orthogonality. They did this by carefully managing frequency channels using methods like frequency division duplexing or time division duplexing to keep the signal separated either in time or frequency. But here's where 5G brings a game changer to the table. Instead of sticking to the old ways, 5G networks leverage something called as the spatial multiplexing. It's like having a bunch of antennas at a transmitter all working together for parallel data transmission over the same time and frequency resources. This innovation allows for a better resource utilization and higher data rates compared to the older networks. However, there is a twist in the story. Spatial multiplexing isn't without its challenges. One of the most formidable opponents it faces is interference, which can sneak in from nearby users and neighboring cells. So, in this video, we are going to take a deep dive into the world of interference in 5G networks. We will unravel the different types of interference, what causes them, and how they play a part in the performance of the entire system. Moving on to the experimental part of this video, the first observation we are going to make is to examine the SIR and SINR while incrementally increasing the transmission power across three different intersite distances of cell. So, three different intersite distances necessarily meaning three different cell sizes. This is how it's going to go. First, we will have a constant ISD, and for that constant ISD, we will check out the SIR SINR behavior for three different transmission power. It's followed by incrementing the cell ISD and again checking it out for three transmission powers, and so on and so forth. The first ISD, constant ISD, we are going to keep is 200 in an urban macro scenario, and the three powers we are going to be checking out for are 23, 33, and 43 dBm. Now, we have for a constant ISD graphs for three different transmission powers. We can take a look into this. The SIR remains pretty similar despite the increase in transmission power. Why? Basically, if you look at the formula, in the numerator, while you have the signal power, you have in the denominator the interference power. So when you do increase the signal power, remember that the you increase the signal power for an accompanying transmitter also. Therefore, causing an increase in the denominator and numerator proportionally, which cancels each other out numerically. Therefore, we can explain how the curve remains similar for increasing transmission powers. But SANR is totally different, where you can see a increase in the performance for when you increase the transmission power, because this the SANR improvement can be noted in a noise limited scenario. A noise limited scenario is a scenario where the main reason for noise is the thermal noise or the device causing noise itself. And to further make more inferences, we will continue the same observation for another ISD, that is 500. Okay. Now we have completed the simulations of three transmission power for a higher ISD, which is 500. And this pretty much follows the trends that were earlier seen in the previous ISD also. But one noticeable difference is the more pronounced difference between three different transmission power. That is, increasing the transmission power increases the SINR performance as the cell size increases. In other words, the increasing the transmission power does not work well in smaller cells. So what is the reason? When the cell is larger, the effort it takes for the interfering signal to interfere with the neighboring cell is more, thereby causing a lesser interference than in cells which are small and nearby. If you tried for 1732, you could see even more well pronounced SINR graphs. Thereby, we are concluding the first observation with two sub observations, that is, when you increase the transmission power, the SIR remains the same and the SINR improves in noise limited scenario. The second observation is the SINR improves better in larger cells than in smaller cells. Thank you. Moving on to the second observation, now we are going to change the geometry of the user equipment arrangement and see the effect it has on the SIR and SINR. And by geometry, what we are going to do here is increase the minimum distance between the base station and user equipment. So if you increase it, you make all the user equipments move away from the base station towards the cell edge, and this can be done by increasing or decreasing this minimum distance parameter in the system parameter options. So similar to previous observation, we are going to check for three different intersite distances. Let me start with the intersite distance of 200 and a minimum distance of 10 and proceed from there. In order to get a well defined curve, I'm using a number of user equipments to be 1000. Based on the capacity and performance of your system, you could do the same or increase or decrease, which you feel appropriate. uh, and we have completed the simulations required for this of making an observation and inference. Taking the SANR graph into account, it can be seen that this is the one for a minimum distance of 10 between the 10-meter between the base station and user equipment, and this is minimum distance of 100-meter. We can see that as the user equipment all get distributed more towards the cell edge, the performance deteriorates. This can be attributed to the fact that when more of the user equipments are gathered or distributed around the cell edges, the effect or impact of interference will be multiple fold than the previous one where they were distributed throughout the cell. And this is the reason why when we increase the minimum distance, we experience more interference. Now let us repeat the same for a different ISD. Okay, now the simulations required to make the next observation has been completed. And if we notice the parameters in question, which is the SAR and SANR CDF graphs, you could notice that follows the same rule as the previous observation for 200, but the curves are more steeper, meaning the cells and SANR performance is more sensitive to user equipment distribution as the cell size increases. The same can be noted if you increase the cell intersection distance to 1732 as well. This concludes the second observation, and we'll be moving on to the next one. Moving on to the final observation, where we are going to change the terrains and different intersect distances within each terrain and observe how SAR, SANR curves exist over there. For this, let me start with the urban macro for different intersect distances of 200, 500, and 1732. Now we have completed the simulations required to make this observation. Let me move on to the SAR, SANR parameter curves. And if we can separate out the CDFs over here, and I want you to focus on the SANR graphs in specific. And you could see the increase in SANR deteriorates the SANR, increase in the ISD deteriorates the SANR performance. But it's quite contrary to what we discussed earlier. And this is where I would like you to take a deep look into the equation where the numerator is signal power and denominator is interference power plus noise power. While yes, the effect of interference power is less pronounced when we move to a larger ISD, so is the impact of signal power. Imagine in a larger cell, users in a larger cell, the users which are far away from the base station, they experience a very less signal power. So when because of this reason, the graphs which are based on averaging, we could see that as the size of the cell increases, the SINR performance deteriorates. Now that we have made this analysis for the urban terrain, let us repeat the same but for a rural terrain. Okay, let us make the final observation. It has been a quite a long road now. So if we could separate out the CDFs and notice the behavior of the SINR graph over here, you could see two observations. One is generally the rural macro at each cell intersect distance outperforms its urban counterpart. This is because the rural terrain in general has a better SINR performance than the urban due to the favorable propagation scenarios in the terrain. And another one is we could notice urban being more sensitive to the cell size than the rural terrain. Now, these three observations that we have made will give you a much better picture of what interference is and the role it plays in a 5G network. For any questions or problems regarding the implementation details, you can contact the Jigyasa team. I will meet you again in another video with another wireless concept. Thank you. Clarification.